The describing motion, a break from Aristotle. Roughly 2,000 years ago, maybe a little bit longer, Greek natural philosophers were thinking about very hard about the world that they lived in the natural physical world, and some of them were making observations, some of them are thinking about how the world should work. By and large, they were doing philosophical study, natural philosophy, and in the course of their efforts, they established a lot of important ideas, some of which are part of the classical physics or even modern physics. And yet, I cannot call what they were doing classical physics because they were really missing an essential ingredient. The scientific method was still not present. They weren't being systematic in the approach. They were reflecting on how this thing should be or seems to be, but are missing this idea of testing and formulating theories. I would like to go back 2,000 years ago and talk about a little bit about some of the key ideas, and in particular, one of the key players, Aristotle, who was one of the most influential Greek natural philosophers, and his ideas about the world have been influential for a lot of reasons. In fact, many people today continue to hold Aristotelian ideas about how the world works, which is quite natural if you don't investigate carefully or scientifically. And what we will find is that it took over 1,000 years before somebody, namely Galileo, who we are going to talk about today, decided to challenge this idea of Aristotle with some very simple, very elegant experiment. And in fact, one of my favorite experiments of all time, rolling little marbles down an inclined plane. The rolling little marbles down an inclined plane. There are an awful lot to say about such a simple little experiment, and today we are going to really focus on what we can learn from doing that kind of experimentation. So let's talk about a little bit Aristotle ideas first, so that we can understand what it was Galileo was trying to make sense of there and try to change. Aristotle lived in about 3000 BCE. He's thinking about religions, he's thinking about biology, he characterized a number of the physical systems with observations, and as a contemporary physicist, when I look back and think about Aristotle's study of the natural world, it seems somehow murky to me, and it's a little bit confusing, and so it's worth trying to make sense of what he was saying. The part of the reason it is murky for me is that, of course, I have my contemporary classical physics way of thinking about things. Trying to imagine how you could view the world in this old way, in challenging but perhaps informative. Also, Aristotle watches things. He just he looks just around the world, and it seems to me like every object has a natural place. Just look around you. If there is a chair, its natural place is on the ground. If there is a very heavy object, its natural place is down or even in the ground. Maybe light objects belong to up in the air, and feathers or dust or smoke belongs. Which up or smoke have a natural place which is up in the air, and then you look. If you look up the sky, you see them. You see the sun, moon, and stars. You say, "Oh, those are something totally different and obviously not part of our natural world. They are some sort of mystical thing, possibly religious, possibly who knows, and they seems to be ideal. They seems to be little perfect dots and circles. Now Aristotle is not experimenting, he's just thinking about how it seems like things ought to be. And part of the problem was that he wasn't being careful in defining what it was and that he wanted to measure. So if you're talking about motion, that's a vague word. And what we are going to think about in the today lecture is how you might be a little more rigorous about. Oh, sorry, I skipped the sentences. If you are talking about motion, that's a vague word, and what we are going to want to think about in today's lecture is how you might be a little more rigorous about defining something such as motion, or what you mean when you say faster or slower. In fact, it will be both in this lecture and next lecture where we want to work out those ideas. I call these operational definitions. If you're going to use the word and you want to talk about how the natural world is, then you need a definition that is not philosophy. We need to be able to define our words by what we do to measure them. What kind of experiments or steps do you have to take in the order to, for instance, distinguish between the first object and the object that is accelerating. We often use speed, velocity, and acceleration as informally as motions, and we are going to want to firm that all up. Velocity. If you don't firm it up, then you probably go through life as an Aristotelian, and that's not disaster. He was a smart guy, but it's an examined and only personally correct worldview. In the end, if you start to think about things, you find that Aristotelian worldview is unsatisfying. So let's continue back to this idea of the natural state of the things. If you believe that objects have a natural state, what if you perturb them? What if you perturb them? For instance, if you push a cart and you let it go, and Aristotle knows what's going to happen, it's going to grind to halt, and at least if it's on the flat load or any kind of load, that cart is going to come to the rest. So Aristotle would argue that object comes to the rest because it's a nature of the cart to come to rest. So he's attributing the attributing the cause to the object itself, which is a funny way of thinking, but not entirely unreasonable. Now think about heavy object and light object. If you drop them, then we mentioned this last time. Aristotle is thinking about which one is going to hit the ground first, and it's completely obvious to him, because the heavy object has a natural tendency to be on the ground, which is much stronger than the light object. So he writes that's clear that the heavy object would strike the ground first. He believes that it's a fundamental nature of the object to do so, so you don't have to why. He's not really asking the question why or for an explanation. He just thinks he's describing the nature. If an object is in motion, Aristotle asks questions. What is that keep it in motion? What is it that keep it in motion? If a cart is moving, why does it keep moving? It seems like a natural question. Aristotle is puzzling over this, and it turns out, interestingly, that this is an unproductive question. In fact, it's the long question, and so we are going to have to come back and rephrase the question properly. And I'm just trying to establish the sorts of things that Aristotle was thinking about. He has a philosophical outlook, which is that the world can be understood by contemplation and maybe observation. He's certainly not going to object to watching the real world, but he doesn't want to dirty his hands and do experiments. that's not the way he thinks that we should need to proceed to understand the world. And I don't know if I find it kind of remarkable that it took the world 1,000+ years before somebody just picked up some objects and dropped them in order to try to test Aristotle's ideas. So we'll have to come back to that. Okay, the person who is the most famous for doing it is Galileo. Galileo is certainly not the first, and it's a little bit unfair for me to attribute everything to individuals. It's part of my historical oversimplification to talk about some of the key players and big ideas. We are talking about late 1500s, nearly 600s. It's Italy, and Galileo is a part of the Renaissance. He's beginning to challenge some of these old ideas. He's a sharp-witted, brilliant young character who loves to argue. He's always fighting with people. I would love to encourage you to read some more about Galileo. These are lots of delightful biographies of this character, and as with many of the people we are going to talk about in this course, it's a lot of fun to learn about the world he lived in and what it took for somebody to really challenge established world views. So it would take us a little bit too far afield from the physics content to spend a lot of time on these characters, but I encourage you to do so yourself. Realize that the world that Galileo lives in is changing radically. There are new ideas. They are rediscovering old ideas from ancient Greeks and from the Arab world. I am not sure if it was global European inferiority complex, but people seem to think that the ancient ideas were the wisdom of the ancient times and must be correct. They seem to contain everything. And it's just a question of correcting old writings. So it's a shift in the worldview to challenge that, and which is one of the things Galileo ended up doing in part. His rolling marbles down an inclined plane epitomized the kind of experiment that you would want to do to question what Aristotle would be saying about the nature of the object and the motion of the object, and what nature is, and how you develop a language to talk about it. So Galileo he's a true Renaissance man, both literally and in the sense of that we use that today. His insights were not just about marbles on the inclined planes. He was looking at astronomy, and he was thinking about motions and time, and he was thinking about relativity. In fact, the theory of the relativity is really attributed not to Albert Einstein, but to Galileo, and we'll talk about a little bit about it in this lecture. And the next couple of lectures, there were lots of big ideas of classical physics being developed by Galileo. This is still pre-Isaac Newton. We are laying groundwork here. In this lecture, I'd really like to focus on the meta themes. Meta meaning I'd like to step a little bit beyond just the physics itself. I would like to look at the scientific ideas, the methodology, rather than the physical principle. We'll focus we'll focus on the physical principle more in the next lecture. For instance, Galileo is telling us collectively we should do experiments. If you want to test something, you should measure, you should use the tools, and you should develop some kind of standards. All of these are ideas that we all of these ideas that we just take for granted, it is part of what we think of when we think of science today. It's the heart of the scientific method, and Galileo was recognizing that if you want to make measurements, you should really pick a phenomenon and decide what it is that you want to study, and then isolate it. It's a brilliant idea. It's one of those great ideas of the classical physics. You should be able to watch something and describe it. So that's our first step towards science, being able to describe something carefully, accurately, being able to reproduce experimental measurements. And so Galileo was thinking about motion, and he said, all right, we have this problem. When I dropped objects, they accelerate very rapidly, and gravity is down strong. So, and the gravity is down strong. How I'm going to study this idea of Aristotle, who said, obviously, heavy things and light things fall at different rates, and there are a couple of ways you could imagine proceeding. Now imagine it's 1500, and you want to study this question. You'd like to weaken gravity, but of course you can't. There is no knob to turn in experiments to turn off the gravity. And one of the great ideas of the Galileo was to create little artificial environments in his laboratory in which gravity was effectively weakened, and that is this inclined plane. Wow. If you drop something, it accelerates very rapidly, so rapidly in the 1500 it just hits the ground. It's hard to measure, but if something lowers slowly and then faster and faster down the ramp, you can really make some precision measurements. This is part of the story of what Galileo was doing, and indeed, those measurements were critical. So if you want to talk about the motion, you would better be able to measure the distance, and you better be able to measure a time. For distance, well, you have some sort of for distance, well, you have some sort of standards. You can have a ruler. Time is tricky. So imagine what it's like in the 1500s. There is no modern clocks then. In fact, Galileo is one of the people who helped invent the pendulum clock. That is one of the things that we really want to be talking about so much about. He's famous for. How are we going to measure the timing? One of the way he make a timing. And he had lots of creative ideas, and one of the way that he measured things was just to listen to his own heartbeat. Boom, boom, boom. You time your heart rates, and you can use that as a clock, of course. But of course, it's if you are excited. If you are excited about physics that you are measuring, that's not going to be the best clock. So you have to you have to think about more rigorous idea. He had two very clever ideas. One of them involved water droplets. He didn't invent this, but he used it to great effect. You have a little tub of water. You have a little bit tub of the water, and the water drips out of it and drips out at a regular rate. And you collect the water in a pan, and you weigh the pan. This is timing measurement that makes use of our accurate weighing device. Wow. This is again a part of the idea of the modern science is to make some sort of operational definition of how we gonna to measure a time, and may involve other things that we can measure equally well or even better. The other trick that Galileo used was to lay little strings across the track and listen, and he would hear the marble as it rolled down the inclined plane, striking the strings. Wow. And he was very musical, so he could hear when the rhythm was steady, and so it didn't matter so much it didn't so much matter what the steady rhythm was, but that it was a steady, which was part of the measurements that we are going to be talking about.